Hello, everybody. My name is Elle Yan, and you can call me Elle. I'm from University of Missouri, Columbia. I'm very honored and happy to be invited as one of the speakers for this microfluidic webinar, and I would like to share with you for my work, which is titled with Enhanced Water Capture Capability and Regulated Condensation Droplet Distribution. All of them are induced with the electrowetting-on dielectric. And let's get started. First of all, I would like to have a brief introduction about the electrowetting-on dielectric. It's a relatively long term, and I usually call it electrowetting, and I will call it for abbreviation in the following slides discussions. So electrowetting-on dielectric is a very popular method people have been using to control the surface wettability or the droplet shape in many of the microfluidic applications. The magic way to use it is just we can control the surface wettability or the shape of the droplet by applying electric field. Because there are many ways to change the surface wettability. People have used many surface treatment with different chemicals and change surface wettability to either hydrophobic, hydrophilic, super hydrophobic, and super hydrophilic. But once they have treated the surface, it's actually fixed. It's not like reversible or changeable unless you use a new sample. But the good thing for electrowetting when we are doing the following discussion, you can see there is a magic part. So a brief introduction about the electrowetting-on dielectric sample or system, how it works. So it actually started with a conductive substrate. On top of the substrate or a layer of conductive material, you have a dielectric layer. This dielectric layer is to make the whole device to perform better, to decrease the voltage and increase the safety of the experiment. Also, it can make the device last longer and a longer utilization period. On top of the dielectric layer, there is usually another layer of hydrophobic layer. It's either spin coated or deposited with different method. The reason for a hydrophobic layer there is with this hydrophobic layer, we'll actually have a low surface energy, which means any change of the shape of the liquid on top of the hydrophobic layer will be easily detected and observed. So the hydrophobic layer will make the contact angle of the droplet to be larger than 90 degrees. So that's why we see if we try to seed a droplet on top of the hydrophobic layer, we'll actually see the black dotted curve there. So how do we change the liquid shape or the surface wettability by electrowetting? We firstly insert a pin into the liquid, and then we connect the other end of the pin to the conductive substrate. In between them, we'll try to apply voltage there. Without voltage, so this is the initial shape, which is a little bit like hydrophobic shape and larger contact angle larger than 90 degrees. But what if we turn on the voltage? So we'll see a contact area become larger, which means the liquid shape becomes flatter. And the contact angle is also decreased. So the initial contact angle is like this, which is larger than 90 degrees. And then after we apply the voltage to the system, or actually to the liquid, the contact angle will become like this, which is much smaller. So this is how we control the surface wettability using electric field. This is another way of wettability change. So I mentioned a magic way about this one compared with many chemical treatment. The magical part of this is actually this is reversible. So if you don't want the liquid to be flatter after like you have applied some utilization or manipulation of the droplets, then you want to let it just recover to its initial status. The only thing you need to do is just turn off the voltage and make it back to U equals 0, and the shape of the droplet will shrink back to its initial hydrophobic or larger contact angle status. And this is a very good thing because it's actively controlled and also it's reversible. And the voltage, applied voltage is also affecting the change of the contact angle. So the change of the contact angle is actually following the Young-Lippmann's equation. Theta 0 or theta naught is the initial contact angle, which we observe from here. And epsilon naught, epsilon d, this is a vacuum permittivity. It's a constant, and this is the dielectric constant of the dielectric layer. Once you have a certain material fixed, then this is also a constant. And the sigma is actually the surface tension and of the liquid and gas. You can use like salt water, you can use DI water, and the surrounding you can use air or other type of gas. So this is also fixed when you're doing a certain experiment. And D is the thickness of the dielectric layer, and this is also fixed when you fabricate the whole system or sample. And the only thing that's changed is theta and the V. So you can see the larger voltage we apply to the system, the theta is becoming smaller. And that's meaning the surface or the droplet is becoming flatter and flatter, and that's reasonable. So this is a basic of the electrowetting that help us to get familiar with the discussion for our today's topic. Next, I would like to introduce some more electrowetting devices. Previously slides, we have observed a pin inserted into droplet setup. And what if we want to have an open plate, and we might have instead of just one droplet, we might have several or multiples droplets, and we want to control them. How do we do that? So there are actually two types of open plate electrowetting devices. The first one is called we can call it a coplanar because we placed the two electrodes to be parallel with each other. How will this work? If you can imagine, if we turn on the voltage in between them, say this is grounded and this one is like positive something, then there will be electric field coming across. So it's actually the electric field is shooting from one electrode to another one. When it's shooting from one to the other one, the electric field is coming through the droplet, which make the droplet to be affected by the electric field. And as long as the droplet can be affected by the electric field, then the electrowetting effect will happen. So this is one setup. And the other setup is instead of placing the two electrodes to be coplanar, to be in the same plane, we try to place them to be double layer. So we have a conductive substrate as well, but instead of placing the one beside it, we place the positive one, or we can place this one, call it ground, or call it positive voltage one, because you can actually flip them. So the other electrode can be a smaller size, but on the top layer. Why this can happen, why this setup can make the electrowetting happen as well, is because as long as you turn on the voltage here between this electrode and the bottom electrode, there will actually be electric field shooting upward and then go back to the substrate. So in this case, there will also be electric field coming through the droplet. and that will also make the surface tension, surface or the energy distribution inside the droplet change, which makes the shape of the droplet change as well. So that's something people have done to improve the setups instead of having multiple pins inserted to the droplet. So with the open plate device design, we can manipulate the droplets better, or we can manipulate a larger number of droplets. Next is a brief introduction about our test design. So we have utilized the double layer design, and then for this setup, we started with a conductive silicon, and then on top of the conductive silicon, there is a layer of silicon nitride, which is dielectric layer. On top of the silicon nitride, we use the photolithography to design this gold layer. After we have the photolithography and the sputtering and the lift off, we have the electrode shape we want. On top of this gold layer, we deposit another layer of silicon nitride, rather than just use a hydrophobic layer on top of that. The reason for this is to increase the safety of the whole device and improve its utilization period or its lifetime. On top of the last silicon nitride layer, we spin coated a layer of Teflon for a hydrophobic layer. So with this setup, we will try to do more studies on the electrowetting effect on multiple droplets. One thing to mention, so the left-hand side figure is a top view of our electrowetting pattern. So if we cut just like somewhere here and take a cross-sectional view, then we'll see this. So this gold is the whole layer of the electrode. Why we are designing the grid is because we want to make as much area as the electrowetting effective area is, so that we can observe the electrowetting device, like the effect, how it will behave for our following studies. And why we are doing a side-by-side or a mirror-size design is because we want to do a comparison. So we'll keep one sample, for example, the left-hand sample, to be with no electrowetting, just for comparison. And everything on the right-hand side is exactly the same, but the only thing that's different is with electrowetting or with voltage, so that we can do more study on the comparison. Next, a brief introduction about the experimental setup. We'll do a side-by-side study, and all the samples are fabricated under the same procedure. Only one will be charged, and the other one is just for comparison. And the two small beakers are just to collect more water and see how much water the different samples can be captured. And the left-hand side is basically overall view of the setup. So we have a camera to capture the dynamics, and this is a ring light to shoot more light towards the testing surface and for better visualization. And this is a testing area which is enlarged at the right-hand side. And the samples are insulated with a PDMS. So this PDMS is to make sure the electric field on the right-hand side is not affecting the left-hand side at all. Also to insulate them for any other unnecessary interpolation. All the two samples are attached with a thermal paste to a cold plate, so that we'll have the surface to be cold enough, and then we'll supply air mist towards the surface. And based on the humidification difference and the temperature difference, there will be water droplet formed on top of on the surface, on the condensing surface. Next, I would like to share with you about the result, what we have found. Firstly, we tried to see if we turn on the voltage suddenly, what will happen. And as you can see, the right-hand side is under electric field effect. So the right-hand side on the first row is when we suddenly turn it on, what will happen? As we can imagine, or if we remember, so this is the initial status of the droplet when there is no electrowetting effect. But when it's turning on, it's becoming flatter, so there will be stronger interaction with the surrounding droplets, and that will make a strong coalescence and faster droplet growth. And the droplet will either grow to larger droplet and become larger and spare some more space for a new cycle of nucleation or water capture, or either it will just be the formed droplet will be large enough or heavy enough to shed off from the surface. So this is what we have observed when the droplet, when the electrowetting is suddenly turned on. So this is what we can see. Another thing is, what if we keep the electrowetting or the voltage to be on all the time? Say it's flatter for a longer time, but then we suddenly turn it off. Then we know that the droplet will bounce back. It will just shrink back. So this type of dynamics is also making the interaction for the droplets with its surrounding droplets, and the strong coalescence, the strong oscillation of the interaction will make a strong coalescence. Also, when the interaction is strong enough, then it will form a very large droplet and finally shed off from the surface. So what we can learn from this is we actually utilize the interruption of the electrowetting effect, and we can increase the growth rate or the shedding off frequency. It can shed off earlier than the natural status of the surface. So that's basically what we have firstly found from the water capture part. And with this, we know there will be a faster shed off rate. So that's meaning there will be a faster growth cycle, or its growing period is shortened and it's more efficient to capture more water. Next is what we have found for a longer real-time speed. So this is a real-time speed compared with the last slow speed motion, and we have tested it for a longer time, for about 8 minutes, and we tried to observe the difference, the water capture difference, using the droplet detection method. How we do that? Firstly, we see the air mist from bottom to the top and to the condensing surface, and we make sure the condensation is equally distributed, and that's why we have a TC there. So when we see there is a relatively equal distribution of the droplet, and then we suddenly turn on the voltage, and then after a certain period, we will observe what will happen. So here we see the black parts are the water coverage of the droplet, and the red dotted dots are the no electrowetting surface. And we can observe that for the 20 and 60, there are a faster shed off, earlier shed off of the electrowetting. Also, we see every time one is shed off, it's clearing the surface much more than the normal surface. Even though we see a relatively slower shed off of the 40 volts, but we actually see one more time of the shed off in the same almost the same time period for the 40. So this will make us like a better understanding for water coverage or the area of the droplets on the surface. And it's actually indicating a better water capture capability of the electrowetting devices. Besides utilizing the image processing, we do a real test for water capture study. And we did the 20, 40, and 60 volts comparison and found that the water collection rate are improved with a 138, 171, and 220% respectively under the 3 voltages. This is very inspiring. It's very exciting thing because it's actually showing a very good promised method for energy saving and water conservation. So under the electrowetting effect, we know the water is captured faster and collected faster. It's having a faster or better growth rate and efficiency. So this is a water capture enhancement study. And next, since we have done some air mist flow through the surface, we know that as long as there are droplets on the surface, and if we turn on the voltage or the electrowetting effect, we know there will be a faster droplet growth rate and a faster droplet shedding off rate. And then what if we just put our device in a chamber, a condensation chamber filled with water vapor? And this is our next step. And that's how we find our regulated droplet distribution. This time, rather than only using the grid design, we tried different types of design as well. For this double layer design, we have A, B, C. The first one is a thick wire design, and the second one is a thin wire design with only vertical wires. And we still use a grid wire design with both horizontal and vertical wires. And next, we also try to use to design a coplanar device. And the coplanar device, we know the most effective area is in between here because there will be a more intensive electric field in between there. So the droplets trapped in this region will be affected obviously under electrowetting effect. And this is a top view of our design, and these are the regions for the gold or the electrode. And you see the zigzag, the dark region or this gap region is actually the electrowetting effect area. So why we are designing the zigzag is because we want to enhance or increase the contact area of the effective electrowetting area. Next, a brief introduction about the experimental setup. So this time we also do a side-by-side comparison, and our chamber has several holes to have our wire going outward. So we will either put the charge sample on the left or the right, so that we need to have the wire outlet hole. And beside that, we also add a hole to insert the thermocouple to help us detect the temperature of the water vapor inside it. And we also use a pressure transducer here to detect the pressure, so that with the temperature and the pressure of the inner water vapor, we can calculate how much water vapor or how pure the water vapor is inside this chamber. And we can also analyze how much non-condensable gas is mixed inside. And a brief diagram from a side view is shown on the left-hand side. We will still have a high-speed camera for visualization, and there is a front cover I didn't show there. So the front cover is also made of stainless steel, there is a visualization window, which is heat-resistant glass, so that if we try to heat up the glass and do some visualization, it's like reliable enough for multiple times the experiment. And C is a test chamber, which we can see here. And E is actually the copper block. So from here we see there are two copper blocks. They are insulated with a PTFE block. And this is similar with the PDMS block, like piece we have seen in the previous result. So this is first to insulate the electric field effect. The other reason is to insulate the heat transfer, so that there will be the heat transfer in between the two copper blocks are just separated and they don't interfere with each other. On the back of the copper block is actually there will be cooling water running through it to cool it down, so that there will be a temperature difference from, like, this is a low temperature and this is a high temperature. And then inside it is relatively high but still low, so the vapor temperature is very, very high. So the TV is the highest. There will still be a temperature difference on in between the sample and the in between the condensing surface and the vapor. And this cooling water is cool down the block and cool down the sample, so that there will be enough temperature difference for condensation. Next is our cycle or a loop or our system. So we'll start with the steam generator to generate steam and supply it to our test section, which is shown in the last slides. And we'll have temperature measurement and pressure measurement. For the uncondensed steam, we'll do an uncondensed steam treatment so that there will not be any burning happening, which is very dangerous for the experiment. And finally, we'll drain the steam, uncondensed steam, and make it condense as much as possible. For the cooling loop, we'll have a cooling machine to pump the cold water and cycle it. In the cycling piping system, we'll add a flow meter to detect how much water is running through, so that we can calculate the mass flow rate of the cooling water. And the cooling water is running through the copper block and cool down the copper block as well as the condensing surface, so that we'll have enough vapor generated. And next is our result of the regulated droplet distribution. So the A, B, and C are the double layer design, which we have electrowetting effect on the right-hand side. And the D is the zigzag or the coplanar design. We have the electrowetting on the left-hand side. Here we can see when we turn on the voltage, for example, if we can see the C, the droplets are like distributing in between the electrode wire. Also, if we see A, the droplets are distributing very regulated, like a chessboard, and sitting inside the grease. And if we see here, so when we turn on the voltage, the droplets are coalesced strongly, and they tend to be squeezed inside this channel in between the electrode. So this is actually definitely very obvious condensation distribution difference. And we can take a look again. So all of them are in the same testing environment, but the only thing that's different is the electrowetting effect. So right now we can see a very obvious distribution effect. For example, this one, and this compared with the left-hand side is having a faster growth rate and larger droplet size and more regulated droplet distribution and faster, also like a relatively larger droplet size on the left-hand side. And this one we see along the zigzag shape, the droplets is aligning vertically. It's also very regulated compared with the right-hand side. So that's pretty much all the thing I would like to talk today. To conclude, so we have described that electrowetting device that can enable a separation between the droplets and the electrodes. So that's the startup of our study. Why we need to start with that? Because we have multiple droplets which are growing and growing, so that we can never utilize certain pins to track them. But with the open plate design, we can have droplet growth, droplet coalescence, shed off, renucleate. So that's possible for our study. And then we observe the phenomena when we turn off and on the 60 volts. And we see that the electrowetting is changing the droplet morphology a lot, and it will make very strong coalescence and even droplet shedding to clean the whole surface. And we also do a side-by-side experiment and try to collect the water for 20, 40, and 60. And we have observed that a very passive result, a very encouraging result. And all of them have a very good water capture rate enhancement. We also see that when we enlarge the voltage, magnification, we see a positive correlation of the water capture enhancement as well. Next, as we have done the water capture capability enhancement on the ground, and we try to do more with the condensation. So we tried the grid wire, thin wire, thick wire, and the zigzag designs, and we have seen that the charge devices have a very regulated droplet distribution compared with the non-charged devices. And they have a faster droplet growth rate, as we saw in the previous slides. Also, we see a larger and more discrete droplet distribution. We see more coalescence, and this will make the droplet distribution more discrete, and it actually free up more condensing area for small droplets renucleation and growth, and it also accelerates droplet shedding frequency as well. So this overall work reported here is a very good way for people to consider for many microfluidic related utilization, because it can actively influence the microfluidics on a microfabricated surface, and it's also reversible. So whenever you turn off the voltage, so everything is turning back. So whenever you want to, for example, enhance the water capture rate and the condensation rate, you can turn on the voltage. When you don't really need that, you just can turn it off. So that's a good thing for the manipulation by electrowetting. And that's pretty much all for my talk. I really appreciate your time and your patience to give me this opportunity to share with you some of my work. Thank you very much.